In this video, we're going to go over Hooke's law experiment, and we're even going to give you flashcards. So after this video, if there's key words here that you're thinking, oh my goodness, I never remember what line of best fit is, I never remember resolution, absolute uncertainty, or anomalies, just click the link in the description there, click in your details, and we will send you those flashcards straight away. We want you to be successful. And if you need even more revision, we have a whole page on practical knowledge, okay? Understanding those key terms on my resources. Okay, so again, just click the link in the description and we will send you over those flashcards. So, you need to know all of this for your GCSE physics exam. And these questions, like what is resolution, what is the absolute uncertainty, those questions are coming up more and more common in the past papers. Okay, we've seen these in the last few years. So please make sure you see this video, like it, and share it with your friends to make sure we're all successful. So, Hooke's law experiment. The way I remembered it, you got to think about Captain Hooke, right? So like Captain Hooke and Peter Pan has like a little hooked hand. So Hooke's law experiment is what you're doing is you're hooking little masses onto a spring. So what we have here is we have a retort stand, you see those in chemistry, and we have our little spring. Okay, so we've got our little spring. The first thing we do in the experiment is that we'll always measure the original length. Okay, so the original length means there's nothing on the spring, it's just there by itself. Okay, so if I was to write a method, so I'm going to put my method here for this experiment, the first thing we're going to do is we measure the original length. Of the spring. And remember, we're in physics, and they really like it when you state the equipment. So measure the original length spring using a ruler. Okay, so all we do is we take our ruler, we place it here, and what we're trying to do is we're trying to measure the original length of that spring, okay? So I measured the original length of my spring, and I measured that it was 10 centimeters, okay? One thing you want to make sure to do here is that you want to avoid parallax error, okay? So parallax error is another thing called random error, okay? So to avoid parallax error, which is a type of random error, so that means that you might do something wrong. So you want to avoid this type of error. You need to make sure you read at eye level. So for example, if I was doing this experiment and there was my spring, I need to make sure that I'm eye level with the spring when I'm reading off the number. Because if I'm too low and I look up, I might think, like say I'm down here looking up, I might read a number that is too short of an extension. Or maybe I'm much taller and I'm way up here and I'm looking down at the bottom of the spring. I might read a number that's way too long. So I need to make sure that I'm at eye level with the spring, so the bottom of the spring, so I can read what its length is. Okay, so we call that parallax error. Okay, so parallax is a type of random error. And to make sure you don't do it, you always read things at eye level. And you probably see that in chemistry quite a lot when you're reading from measuring cylinders, right? You want to make sure that you're at eye level with the equipment. Okay, so we've measured original length. Now what we're going to do is we're going to hook on the masses. So step 2 is that we're going to attach, or we're going to add the mass to the spring. Okay, so what I do is that here I've got a little 0.1 kilogram mass. All I'm going to do is I'm going to hook it onto the spring. And we know that any time that you put a force on a spring, what's going to happen is the spring is going to extend, right? It's going to get longer in length. So extension just means it gets longer in length. So there is where the spring used to end, right? That was where the spring used to end. But now we can see the bottom of the spring is down here. Oops, sorry. Now we can see the bottom of the spring is down here. Okay? So there's the bottom of the spring. So I want to record that new length. Be careful. Some people always want to measure to the bottom of the mass. It's not. We only care about the spring. We measured the original length of the spring. I want the new length of the spring. So again, a lot of people think you measure from the top all the way down to the hook or all the way down to the bottom mass. You don't. You measure to the bottom of the spring. So again, I have my ruler here. I'm going to make sure I'm at eye level. I'm going to record that new length of my spring. So let's say the new length of my spring was 30 centimeters. So that's the new length of my spring when I attach my mass. So as we add the mass to the spring, 3, we're going to record the new length. Okay, I don't need to say use a ruler again because I specified my ruler up here. Okay, so original was 10 and the new length is 30. Step 4 is to find the extension. So extension just means, extension, all that means there, it just means what is the change in length. So to find the change in length, to find the extension, we just subtract the numbers. So all I'm going to do now is 30 take away 10. So if I do 30 take away 10, I'm going to get 20 centimeters. Okay? But I can see on my table, everything is measured here in meters. So to get centimeters in a meter, I know that a century's got 100 years. So there's 100 centimeters a meter. To get it in meters, we divide by 100. So divide by 100, that's where we get that number of 0.2 as our extension. Okay? So that's that first data point there, 0.2 meters, because that is equivalent to 20 centimeters. 20 centimeters is 0.2 meters. Okay? So we've got the first one. But look, I've done it here 2 more times. So what I need to do, step 5, is I'm going to repeat it. So I'm going to repeat it. I repeated it a second time. I repeated it a third time. And then what I did was I calculated mean. So we're going to say repeat and calculate the mean. Okay, so again, we repeat and we calculate a mean. Then what we're going to do is we're going to attach different masses. So instead of using a 0.1 kilogram mass, I might use a 0.2 kilogram mass. So 0.6 is increase the mass and repeat all of the steps again. Okay, so increase the mass, we're going to change it to 0.2 kilogram mass. And then what I do is that I measure the new length. I subtract the new length from the old length to get my change in length, and I record it in my table. So key thing here is you might think, I just said I added a 0.1 kilogram mass. Why does the table have newtons? Okay, and that's where the next equation comes from. So there's an equation that says, if I want to relate newtons to mass, we can use an equation that says W equals mg. The way I remember it is, what's up my g? So it says the weight is equal to the mass times by the gravitational field strength. Okay? So I want to figure out what the weight is if the mass is 0.1. So if the mass is 0.1 kilograms, and I know that on Earth, it says we're going to use g as 10, so 0.1 times by 10. So 0.1 times by 10 just gives me a weight of 1 newton. So that's how I figured out the force there is 1 newton. So we know when we attach a mass to things, because gravity, because the Earth always pulls things down, that's the force that that mass exerts in the spring. That 0.1 kilogram mass is pulling the string down with a force of 1 newton. If I increase it to a 0.2 kilogram mass, there's going to be a force of 2 newtons pulling the spring down. If I increase it to a 0.3 kilogram mass, there's going to be a force of 3 newtons pulling the string down. So you see the spring is going to be increase in length. Okay. Okay, next point. Next one then is that we want to talk about our table. Okay, so hopefully if you look at our table here, we can see the first thing it says was, I want to know the resolution of my ruler. Okay, so what does resolution mean? Resolution means what is the lowest number that your equipment can read. Okay, so again, the resolution of my ruler is the lowest number that the equipment can read. Okay, so if I look here, I can see everything's got 2 decimal places. So the lowest number it can read is 0.01 meters, right? That's the lowest number it can read, right? Because it's 2 decimal places, right? 0.01 meters, if I want to convert that into centimeters, I can see that I can multiply by 10, multiply 100, that's going to be a 1 centimeter. So the lowest number this ruler can read is 1 centimeter. So what we're likely using here is a meter ruler, right? We're not using a standard 30 centimeter ruler. We're using a meter ruler to measure this, okay? Because the lowest number I can get is 1 centimeter, 0.01 meters, okay? Next but then is what is the absolute uncertainty. You need to learn the absolute uncertainty. The way you calculate it is always you find half of the range. Okay, so you have to remember that. So it says, I want to find the absolute uncertainty in extension for the 10 Newton force. 10 Newton force, sorry, that's misprint, should be for the 1 Newton force. Okay, there is no 10 Newton force clearly. So for the 1 Newton force, which is here, I want to know what is the absolute uncertainty. So what is the absolute uncertainty in my results? So these are my 3 results. 0.20, 0.21, and 0.22. I want to know what the absolute uncertainty is. Now remember, this is not a result, this is the mean. Okay, so that's why we don't use the mean, we use the results that we recorded. We recorded these results 3 different times. We repeated the experiment 3 times. Okay, now I want to do half the range. The range is always the biggest number, take away the smallest number. So the biggest number here is going to be a half, again, of the range, the biggest number, which is 0.22. Take away the smallest number, which is 0.20. So I want to do a half of that range. So now what I'm doing is I'm going to do a half of 0.22, take away 0.21, and that's going to end up with 0.02. So what I end up with is 0.01. That is my absolute uncertainty. So what that means is all of my values are either 0.01 too high or maybe 0.01 too low, okay? So I would call that our absolute uncertainty. It means how sure are we about our experiment? How sure that I actually recorded this to be 20 centimeters. And what we're saying is the uncertainty is 0.01. So it might have been the 0.2 meters, or it might have been 0.21 meters, or it might have been 0.19 meters. And again, the reason why I said here that 20 centimeters is 0.2 meters, but you can see in the table I wrote 0.20 is because all of my data in this table needs to be recorded to 2 decimal places because of the resolution of my ruler. Okay, so we make sure all of our data is recorded the same way to 2 decimal places. Okay, next one here is I've got the word anomaly. Okay, so what an anomaly means, it just means a result that looks wrong. Okay, so something that looks wrong. Okay, so if I look at this table of my information here, I can see 0.2 the first time, 0.21, 0.22, calculate the mean. That's pretty good. Second time, I've got a missing result. Okay, so I'm not really sure here. Third time, I've got 0.62, then I got 0.63, and then I got 0.98, right? So when I added 3 Newton force, when I added the 3 Newton force in my spring, the first time I got an extension of 0.62, second time 0.63, and then 0.98. So clearly something looks wrong there. That is an anomalous result. I recorded a result that is way too large. It's not similar to the other results. So the reason I might got result way too large is I might have not read the scale from eye level. I might have read the scale from way up high, looking down on it, and got too big of a number. Okay? So that's something I did wrong. That's a random error. And what we do with these anomalies or these wrong results is that we need to ignore them. Okay? So you always ignore the anomaly or ignore the anomalous result. So clearly this mean is not correct because this person, they added the 3 numbers together and divided by 3 to get this mean. But that mean then is not correct because they forgot to ignore the anomalous result. So to find the mean here, what they should have done was 0.62 plus 0.63 divided by 2, okay? Because we only use the 2 results then. So in your calculator, if we do 0.62 plus 0.63 and we divide by 2, what I get is 0.625. So again, what we get is 0.625. But again, all my numbers are 2 decimal places, so I want this number 2 decimal place. Because the number is 5 or above, it always makes the number before it round up. So that's why I'm going to record here that my mean is 0.63. Okay? Okay, other things they can ask you in an exam is to calculate the missing result. Okay, so I don't know what I got as an extension the third time. The first time, when I added the 2 Newton force, I got 0.39 extension, 0.44 extension. But I don't know what I got the third time, but I do know the mean. So how do we figure out this missing result? You've got to go backwards, and that's something they can ask you to do as well in your physics test. So we are going to do it over here. So we know if we want to calculate the mean, so I'm just going to pop it down here to find the mean. Okay, what we want to do is that we have to do the first result, which is 0.39. I have to add it to the second result, which was 0.44. We have to add it to the third result that I don't know. Okay, so I'm just going to call this x right now. Same way we do our math classes. So plus x, I don't know it. And then to calculate the mean, we know we have to divide by the total number of numbers. So I add them up and divide by 3, and that's then how I got my mean of 0.42. Okay, now I hope you're thinking the first step here is to get rid of the divide by 3. The opposite dividing by 3 is multiplying by 3 because they cancel. And what you do to one side, we do the other. So the first thing I'm going to do is 0.42 times 3. So 0.42 times by 3 gives me a number of 1.26. So this side is 1.26. So what we did was we multiplied by 3 and divided by 3. So what we're saying now is when we add them all up together, you should get 1.26. So the first thing I'm going to do is 0.39 plus 0.44. So what I'm saying is 0.83 plus x is equal to 1.26. So I want to get what x is by itself. I do the opposite of add 0.83 to both sides. I subtract 0.83 from both sides. So 1.26 take away 0.83 is going to give my missing value of x, which comes out at 0.43. So grand. Okay, next thing then that we could do with our results is we need to plot a graph. So what we need to do is we're plotting a graph of force. So 1 to 4. So there's going to be 0, 1, 2, 3, 4. And we're going to plot a graph of our means extension. So we're plotting this information here. So 0.221426384. So let's say there's 0. Maybe that's going to be 0.2. There's 0.4. There's 0.6. And there's 0.8. And in your exam, you're going to have a graph, right? So you have all those little lines. And they'll have the scale labeled for you. You just need to plot the points. Most of the time, they'll have a few of the points plotted for you, and you just need to plot them 1 point left, right? Because they don't want to waste your time in your exam. So the first one was when the force was 1 Newton, the mean was 0.21. So there's 0.2, 0.21. When the force is 2 Newtons, we got 0.42. So 0.42, 2 Newtons. When the force was 3 Newtons, so somewhere at the 3 Newtons, I need to be 0.63, 0.63. There's where they meet is where I plot my point. And then the next point, maybe they had these 3 plotted for you, so they only want you to plot the last one, which is when it's 4 Newtons, somewhere along 4 Newtons, I need to plot 0.84. So 0.84, somewhere there. So now we can see we have our plots. Sometimes they can actually draw a line of best fit. So what a line of best fit is just a line that follows the trend of your data. So if I was to look here, that pretty much looks like a straight line. So all I do is I take my ruler. So I don't have one, but you can imagine my calculator is my ruler. Oh, I do have one. Ta-da! So I take my ruler, and all you do is you line it across your points until you see a line that looks like your data. So hopefully you can see, if I was to do this line here, that looks nothing like my data, right? That's way out of line. So it's not going to be that line. Okay, when I do my line of best fit, some people might try to do a curve. But look, it doesn't look anything like a curve. So again, that's not what it is. So again, maybe I take my line and I plot it here. Again, that's not a very good line of best fit because all the data points are above it. So that can't be right. Okay, so I want to do a line of best fit that looks like it goes through most of the points, if not all of them. So there probably is a good line of best fit. So I take my ruler and I'm going to make sure my pencil is sharp and I'm going to draw my line of best fit. Okay, so again, you make sure your ruler is sharp and you draw your line of best fit. Now, hopefully you're thinking, if I was to ever see this graph, a straight line that is going through the origin, I know straight away how to describe that graph. Anytime that I see, again, a straight line that passes through the origin is that 0, 0 point, so we call it the origin. What we call that, and the only 2 words to use to describe it, and you actually get 2 marks for this, the only way to describe it is directly proportional. Okay, so directly proportional. And we can even see from the table that the results are directly proportional. Because what directly proportional means, it means if you multiply one number, the other number gets multiplied by the same factor. So if we look at our table, when 1 gets multiplied by 2 to get 2, you can see the mean got multiplied by 2 from 0.21 to 0.42. When 1 gets multiplied by 3 to get 3, we can see the mean went from 0.21 to 0.63. So again, it got multiplied by 3. When 1 gets multiplied by 4 to get 4, we can see the mean also gets multiplied by the same number. It went from 0.21 to 0.84. Also got multiplied by 4. Okay, so that's what a directly proportional relationship means. It means wherever you multiply one number by, the other number gets multiplied by the same factor. And we always see it as a straight line that goes through the origin. Okay? Okay, so looks pretty good. Last thing then is just a recap on what Hooke's law actually is. So Hooke's law says that the force is always directly proportional to the extension. So again, Hooke's law, the whole point of Hooke's law, if I just get my pink pen to summarize it. So Hooke's law, what he said was that the force is directly proportional to the extension, right? We can see that. The force is directly proportional to our mean extension, right? We've got a straight line through the origin. That's what Hooke said. He said that anytime we add these weights, we add these forces onto the spring, the amount the spring extends by, change in length by, is directly proportional to the force we apply. But one thing you have to add is just recognize this symbol. That is how we write directly proportional fast. So you can say force is directly proportional to extension, or a way to write it fast is kind of like a fish. Okay, it's just like a little symbol. That's how we represent directly proportional. But Hooke's law actually said the force is directly proportional to extension up until, just going to get rid of this, up until the limit of proportionality. Right, so what does that mean? Okay, a nice way to remember it is directly proportional, proportionality, right? The birds are kind of similar. So what Hooke noticed, the scientist, he noticed if I keep adding these forces, if I keep adding mass and weights and pulling the string longer and longer and longer, eventually the string gets deformed, okay? Eventually it becomes inelastically deformed. So what that means is the word deformed just means change shape. Inelastic deformed means that when I let go, I take all the weights off, it doesn't go back to its original length anymore. And most people know that maybe with your hair bubbles. So if I stretch my hair bubble too much and I let go of it, it never goes back to its original shape that I bought it. It's a bit longer now. Or maybe you've got those slinky strings you play with. You know those colorful ones? Sometimes you like drop them down your stairs. If I pull it too much, sometimes when I let go, it won't fit back inside the box anymore. Okay? So that's when we went beyond the limit of proportionality. So let's say, again, directly proportional, straight line, straight line, straight line, straight line. But let's say the line starts to curve. What that means then is at some point I've added too much force where the string or the spring will no longer go back to its original length. Okay, it will no longer go back to that 10 centimeters that it started at. Okay, so we can see that when the line starts to curve. And we call that, again, the limit of proportionality. Okay, so we covered a lot in this video. So please make sure, again, just click that link in the description to get those flashcards, to make sure that you understand all of these definitions, all of these words, and how to do these calculations. Because again, these questions are coming out a lot. If you need more help, just comment underneath the video what you want me to do, and always check out my resources. Good luck.